All right, just a recap before we go on to the next exercise. So you can express an interval with interval notation. That's the most concise way. You can express it as an inequality, and you can represent it visually using a diagram, like we did over here in the third column. So on the next page, you can see there's a few more examples, except each of them only has one representation. But there's the other two are left blank for you to fill in. So let's do a couple of these together, and then what I'll do is I'll invite you to just do the rest on your own. Okay, so let's start with the first one. So we've got the open interval that goes from -2 to +3. So that, as an inequality, you would write that as -2 is less than x. You could use any variable you want. You could use y or z. It doesn't really matter. But I'll just use x because that's what we've been doing so far. So that would be as an inequality. This interval describes the set of all real numbers x that lie strictly between -2 and +3. As a sketch on the real number line, we would do it like this. And I'll, just to keep with the convention, I'll just draw the labels on top. So I'll put -2 here, and I'll put +3 here. I'm going to want open dots. Oh, that one's a bit sloppy. I want open dots, and then we're going to shade everything in between. Okay, so that is a sketch of the open interval. What about this one here? The second one is expressed as an inequality, but it's not like it's a variable x, but it's not sandwiched between two values. It's just, it says greater than or equal to -4. Well, remember, if there's only one endpoint, that means you're going to have your interval that stretches on forever. So the only restriction you need to worry about is that x has to be greater than or equal to -4. Let's start with the illustration. So let's plot -4 on this number line. And what are we saying? We're saying that x has to be greater than or equal to -4. So the numbers that are greater than -4 are the ones that lie to the right of -4. And if there's no upper bound, it's just going to go on forever. So I like to shade them like this. You could add the other arrow too if you want, but I just, out of habit, this is the way I like to draw them. Okay, and then now you ask yourself, do we include -4? The answer is yes, because this inequality is non-strict. So we're going to include this one. And there we go. Now we've got the visual representation. And how do we write this in interval notation? Well, we're going to have a square bracket for our lower endpoint since we are including the -4. But since there's no upper bound, we're going to use the infinity symbol. Remember? And you always use a round bracket if you use plus or minus infinity. Okay, so that's the first two examples. I'll leave it to you to finish in the rest. So what I'm going to do now is I'm going to end this clip here. I'm going to fill in the rest, and then we'll resume, and you can compare what you have to what you see. Okay, so I'm hoping now that by this point you've taken some time to give yourself a chance to fill in this table on your own. And if you haven't, well, then do so, right? Stop the video, go try it, and then come back. But from now on, I'm going to assume that you've already done that, and I'm going to fill in the answers so that you can compare. Okay, so, and I've added some lines here just to organize things a bit, make it a bit easier to read. So take a look at what you've written for your table and take a look at what I've written for the table and make sure it's the same. And if there's any discrepancies, well, take a second look, right? You may want to make some adjustments. Now, if there's a discrepancy and you look at your work and you just can't see why I've done what I've done, and this goes for the whole course, by the way, if this ever happens, reach out for help, right? Don't get frustrated. There's the Math Help Center. You can speak with your classmates, find the answer somehow, and you can always talk to me, right? And again, this goes throughout the whole course. If you ever run into a situation where something doesn't make sense, don't wait, because then it will just get harder and harder. The longer you leave it, the harder it'll get. So ask right away, get things clarified, and then things will make sense going forward, right? And then always keep doing that. Every time something doesn't make sense, ask. The sooner the better. Okay, so what is our goal here? Where are we headed? What we're going to want to do is, well, take a look at these examples. Actually, this is where you're going to see where we're headed. You can see we've got some inequalities. They're more complicated than the ones that we've been writing down for our intervals. But the idea is we want to figure out which values of the variable, in this case it's x is our variable both times, right? We want to figure out which values of the variables of the variable x will satisfy these inequalities. So in other words, the set of all values x that will satisfy those inequalities is referred to as the solution set. And what we want to do is we want to find the solution set, right? And that's called solving an inequality. So how do you do that, though? So we're going to have to back up just a little bit and say, what tools do we have to actually solve these? So That's what these properties are for. They tell us what tools we actually have. And I'll start using the highlighter because then it doesn't create weird things that cover up other things on the page. Okay, so let's start with the first one. What do we have here? First we have if A is less than B. So imagine that A is less than B. Imagine that that's just a placeholder to represent some inequality that you're working on and you're trying to solve. Okay, but you've also got some other number C. So the assumption here is we're letting A, B, and C be any real numbers at all. They could be positive, negative, they could be whole numbers, they could be fractions, they could be variables, they could be or not. Maybe they're constants. They could be known or unknown. There's lots. The possibilities are limitless, right? They could be anything at all. So this is the inequality that you're starting with. If A is less than B, well, then you can do this. That's what this property is telling you. What do we have here? Now it says A plus C is less than B plus C. Really, that's the same inequality, but just with C added to both sides, right? That's all we're saying here. We're saying you can add something to both sides of an inequality. And, well, what else can you do? Notice that the only restriction on C was that it was a real number. It didn't have to be positive. C could actually be a negative number. And if you add a negative number, that's the same as subtracting. So really, there's actually two properties in one here. I'm going to add a comment. I'll erase this first. I'm going to add a comment here. Because C is allowed to be negative, we can also subtract something from both sides. So let's add that in. So since C may be negative, we may also subtract from both sides. And we say that the inequality is preserved in the following sense. It was a less than symbol here. Well, you're still going to have a less than symbol in the resulting inequality. Okay, so that's two things you can do. You can add something to both sides of an inequality, or you can subtract something from both sides of an inequality. What does the second one say? The second property says if you have an inequality, again, just say assume that A is less than B. Assume that's a placeholder just to represent some inequality that you're working on. Now, now there's a restriction on C. If C happens to be a positive quantity, it's greater than 0, that means it's positive, right? Then I can multiply both sides of the inequality by C, and again, the inequality will be preserved. Notice that, I'm not sure if you can hear that, there's a siren going by, but notice that we started with a less than symbol, and when we multiplied both sides of the inequality by the positive number C, the resulting inequality has the same form. It's still a less than relationship. The only difference is that both sides have been multiplied by C. Okay? And again, there's a hidden second property that comes from this. C doesn't need to be a whole number. C could be something like 1/2 or 1/3, right? And what happens if you multiply by a half? That's the same as dividing by 2. What if you multiply by 1/3? That's the same as dividing by 3. So actually, if you can multiply by any positive number, then you can also divide by any positive number, since division and multiplication can be translated into one another. Okay, so I'm going to add another comment here. So since C may be a fraction, we may also divide both sides. Okay, and that's just a comment about property 2. Okay, one more property. Notice that in this case, that only works if C was positive, right? So what if C is not positive? What if C is a negative number? Well, you can still do it. You could still multiply both sides or divide, but you have to flip the sign, okay? So let's go through this carefully to see what it says. If A is less than B, and now we've got a third quantity C that we're multiplying onto both sides of the inequality. Well, look, we can do AC and BC. So both sides of the inequality have been multiplied by C, but notice that the inequality symbol has been flipped. It is no longer a less than symbol. It started with a less than symbol, but now it's a greater than symbol. Okay, so that's what you have to watch out for. It's a common error to overlook this fact. So let's translate this into a comment here so we don't forget. So when multiplying by a negative, we must flip the inequality sign. And also, since again because c could be a fraction, like in this case it could be negative half or negative 1/3, we could also use this for division. So really it's the same thing would apply to if you're dividing by a negative. So I want to just add one last little comment in there. So you can see the theme. If I add a comment, I'll change the color, but if I'm adding another comment to another comment, and I'll just keep changing the color each time so it stands out. Okay, so that tells you what you're allowed to do. And by the way, notice that all of these properties assumed that you were starting with an inequality of the form where something is less than something else. So A is less than B. Does that mean you can only apply these properties to inequalities of that form? No. You can add things to or subtract things to both sides of any inequality. Okay, so that's what this note here is saying. Similar properties hold if you replace that less than symbol, if you replace it with any of the other three inequality symbols, right? So this one is greater than, less than or equal to, and greater than or equal to. You can have an inequality involving any of those four signs, and you can add or subtract from both sides, no problem. You can multiply by a positive quantity on both sides, no problem. You can multiply by a negative quantity on both sides, no problem, but you have to flip the inequality. Okay, so that's what you're allowed to do. Okay, so I'm going to erase those because I don't think they're really worth leaving. Okay, let's put this in practice. Let's actually solve some inequalities. Okay, so we're asked to sketch each solution set and write it in interval notation. Okay, so first of all, let's worry about finding each solution set. So we've got 3x plus 3 is greater than or equal to 9. Notice that's what I mean by it doesn't have the less than symbol. It has, in this case, it's got the greater than or equal to symbol. Well, that's okay. We can still do all of the things that these properties tell us we're allowed to do. So let's start by simplifying the left-hand side. Let's try to get the x by itself, right? So how about we get rid of that plus 3? Let's get rid of that. So we're going to subtract 3 from both sides of this inequality. So if I subtract 3 on the left-hand side, I'm going to get 3x. And if I subtract 3 from the right-hand side, I'm going to get 6. Okay, great. So that's getting a little bit simpler. Now what I'm going to do, and you can look at this in two different ways. You can think of it as multiplying both sides of the inequality by 1/3, and the goal is to get rid of the multiplication by 3 on the left-hand side. We're doing the opposite operation. So you can either think of it as multiplying both sides by 1/3, or you can think of it as dividing both sides by 3. But in either case, you're either multiplying or dividing by a positive number, so it's really property 2 that's going to kick in, which says we leave the sign alone because 3 is a positive number. That's really what it comes down to. Okay, so we're going to divide both sides by 3, and we're going to get x is greater than, well, 6 divided by 3 is 2, right? So, okay, so x is greater than or equal to 2. That is as simple as you're going to get if we're asked to sketch the solution set and write it in interval notation. So to sketch it, let's do it like this. We've got 2. You can sketch it. And if you're only labeling one number, you can draw it wherever you want, but I'll just put it a little bit to the left side. We just want all the numbers x that are greater than 2. So you want to shade in all of these points. And there's no upper bound. There's no upper limit on x, so you're actually going to get, the arrow's going to stretch forever. And since it's a non-strict inequality, right, it's greater than or equal to, we're going to include the number 2. Okay, so that's your sketch. And in interval notation, you can write it like this. A square bracket around the 2, and then an infinity symbol for the upper bound, since there is no upper bound. And remember, you always use a round bracket for infinity. Okay, so that's all there is to it there. That was our solution. We've got a sketch along with the solution set written in interval notation. So if you're asked for the solution set, it's this thing. This is the solution set. It's the set of all numbers that satisfy the inequality. Okay, so I don't want to take this for granted. What did we actually find here? What are we saying? Like, yeah, okay, we had x is greater than or equal to 2, and we sketched that here. What we're really saying is that this interval of x values is the set of all x values that's going to satisfy this original inequality that we were given. That's what you're really finding here. It's the solution set to the original inequality that we were asked to solve. So in this case now, we're going to look at this inequality. And you can see there's some negative signs here. It's a little bit complicated. We got to go carefully, right? Do one thing at a time. That's the name of the game, and everything will be fine. Don't try to do this in one step. Okay, so what do we got? We got 11 is less than negative x over 2 plus minus 3. Let's just keep it simple. How about we just deal with the minus 3 first? If that weren't there, it would be a little simpler to access the x, right? You want to get the x by itself eventually. So start with the easy things. Let's add 3 to both sides of this inequality. So if I add 3 to the right or to the left-hand side, I'll get 14. And if I add 3 to the right-hand side, well, I'll just get negative x over 2. Okay, so, all right, well then next I can say, okay, well now I want to get rid of that 2 on the denominator of the fraction on the right-hand side. So I can multiply both sides by 2, right? Let's do that. If we multiply both sides by 2, we're going to have 28 on the left-hand side. And if I multiply the right-hand side by 2, I'll end up just getting negative x. Because if I had half of a negative x and I double it, I'm going to get a whole negative x. Okay, and finally that gives us, we're getting close, right? We almost have x by itself, except it's a negative x. We want it just x by itself without the negative sign in front of it. And by the way, notice that I didn't change that inequality sign, right? It was less than here and it's less than here. And the reason is we multiplied both sides of that inequality by 2, which is a positive number. So that's property 2, which says that if you multiply by a positive, you do not change the sign. Okay, so, but how do we get rid of that negative 1 in front of the x? And the answer is we can multiply both sides by negative 1, right? Because a negative sign in front of x really just means negative 1 times x. So if you multiply by negative 1, you're going to introduce another negative sign, which will cancel with the one you already have. So what we want to do is multiply the 28 by negative 1, and that'll give us negative 28. And if I multiply the negative x by negative 1, I'll end up with positive x. So what happened here? I multiplied both sides by a negative, which means I have to flip the inequality sign. So that gives me negative 28 is greater than x. Okay, and again, that's about as simple as you can make it. You may choose to write it in a different form. You could write this as x is less than negative 28, like that. Just flip the sign, but then also have them trade places. These are equivalent. These two. So that's an optional step. You don't have to convert them like that, but you may find it's easier to think about it in this fashion. Okay, but now let's sketch. Let's sketch the interval. So x is less than negative 28, so let's just sketch negative 28, and we want all the numbers that are less than negative 28. So that's going to go on forever. And then since this is a strict inequality, we want an open dot on the negative 28, right? So that's going to be the sketch of our solution set, and in interval notation, we want negative infinity for our lower bound, since it goes on forever to the left, and then negative 28 for our upper bound, and it's a round bracket since we aren't including that point.